There are two spectral corrections to configure, one for losses in the low frequency range and one for losses in the high frequency range. The correction in the low frequency range is to compensate for flux losses because fluxes are computed on a limited time span and possibly because time series are detrended before calculating fluxes. This implies a certain loss of flux contribution that is also dependent on the time constant selected for the detrending method. The correction in EddyPro is a fully analytic correction for Moncrief et al. 2004. No configuration is needed because all the information was provided when the time averaging interval and detrending method were selected, so simply select the correction to apply it. Now let's look at the correction for high-frequency losses. These losses occur for several reasons, including the distance between instruments, the finite volume of the cell in the instruments, the finite time response of the instruments, and the actual attenuation of atmospheric fluctuations, for example, in gas concentration. These are all reasons for the losses at the high-frequency range. EddyPro now provides 4 methods to correct for these losses: Moncrief et al. 1997, Horst 1997, Ibram et al. 2007, and Frattini et al. 2012. Moncrief is a fully analytic method. Basically, this method models both the co-spectra of the fluxes as they should be in the atmosphere, and models the different sources of the attenuation to derive a correction factor that doesn't need any configuration because everything is done inside the model. The parameters to tune the model are taken from the results of EddyPro, so no configuration is required for Moncrief. This method is best suited for open-path systems or closed-path when the sampling line is very short and possibly heated and insulated so that the relative humidity is kept very low in the tube. Relative humidity has a strong impact on the attenuation of water vapor, so if water vapor is of interest, the intake tube should be short, heated, and insulated. Under these conditions, the method of Moncrief is suitable for closed-path systems. The other 3 methods are different from Moncrief and require a spectral assessment file. The spectral assessment is a procedure based on the raw data to calculate the cutoff frequency of the eddy covariant system under consideration. The cutoff frequency is a quantification of the attenuation of scalar spectra induced by the system. So if you select any of these options, the remaining part of the interface activates where you can configure the spectral assessment. Cutoff frequencies are calculated for passive gases, including CO2 or methane. They are calculated just once, so you have one cutoff frequency for the whole data set. For water vapor, however, the cutoff frequency is assessed for different ambient relative humidity classes so that attenuation is quantified differently for different relative humidity conditions. This is because relative humidity has a strong effect on the attenuation of water vapor. So the spectral assessment is done using the spectra calculated from the raw data. During the raw data processing, EddyPro calculates spectra for all variables. This can be used for the spectral assessment. Here you can select which parts of the dataset to be used by setting the start and end date. The spectral assessment is based on ensemble averages of temperature spectra which are used as a reference. Temperature spectra are assumed to be measured correctly because the anemometer has minor sources of attenuation. Ensemble averages of the actual averages are increasingly more reliable and representative of the actual measured spectra when the number of spectra averaged together is sufficiently high. You set the number in the field called minimum number of spectra for valid averages. If there are fewer spectra, then the average will not be considered valid, and the method will not be applied. EddyPro calculates an output spectra for all raw data for all flux averaging intervals. In order to make the procedure more robust, you can set some filters so that specific spectra are excluded from the assessment. This filter is applied to the fluxes, so for example, the minimum of 2 micromoles per meter squared per second means that anytime the CO2 flux is within plus or minus 2, the corresponding spectra are not used in the spectral assessment. This is because typically small fluxes are associated with poorly developed turbulent conditions. This is true for CO2, methane, and the fourth gas. It is also true for water vapor, but to set the water vapor flux, we must provide latent heat flux, which serves as a filter for water vapor spectra. Similarly, for the temperature spectra, the corresponding filter is for the minimum sensible heat flux. This procedure is based on the assumption that temperature and other scalar variables behave similarly. This is known as the spectral similarity of passive scalars in the atmosphere. So, the assumption is true in the so-called inertial subrange in the medium and high frequency ranges. Therefore, EddyPro provides you with the option to select the frequency range on which the spectral assessment should be performed. The spectral assessment is based on the ratio between the temperature and the scalar's average spectra in the frequency range where the similarity is supposed to apply. At low frequencies, similarity may break because low frequencies are associated with slow-pace phenomena on long time scales. At these time scales, phenomena such as sources and sinks of the scalars becomes increasingly important to overlap with turbulent dynamics. What you can observe is that at low frequencies, the scalars deviate from each other in terms of behavior. Similarly, at high frequencies, the measured spectra can deviate because of aliasing or high-frequency noise. You can set the high-frequency range considered for the spectral assessment, so the cutoff frequency will be calculated within the frequency range you specify here with the lower and higher frequencies. Typically, 1 Hz is a good maximum frequency. The lower frequency depends on the averaging interval that you set. We provide default values that are good for a vast range of conditions, but these should be customized according to your data and to the range of your spectra. Finally, because high-frequency noise may disturb this procedure, there is an option to remove high-frequency noise. Here you can set the low frequency at which you think the noise should appear. EddyPro will make linear interpolation of the so-called blue noise starting at the frequency you set to the maximum frequency available and subtract it from the original ensemble spectra. In this way, high-frequency noise is eliminated. If you do not want to remove the high-frequency noise, just set this to 0 and EddyPro will not remove the high-frequency noise. For the method of Frattini and others, 2012, there is another set of options. You can select an existing co-spectra file if there is one available that applies to the current dataset, or you can set parameters and instruct EddyPro to create the file. You can set thresholds that tell EddyPro when to use the models of Ibram 2007 and Frattini 2012.